Welcome. Let's take a look at number 4. So a theater conducted a study on movie attendance. The results are summarized in the table. And based on this evidence they collected, we'll be estimating some probabilities. So under my table here, I have the number of adults that responded and how many movies they see per month. So first, I just want to go ahead and do a total here. So 5 adults said they go to the movies less than 2 times per month, and then 15 in the next category. So if we add all those values up, we will get our N. So in this case, if you add those, we'll get 25 adults in the study. So we'll use this evidence to find the probability of event A. So event A is that an adult goes to the movies at least 2 times per month. So at least 2 means 2 at the minimum, or in other words, 2 or more times per month. So let me just use my probability notation here. So the probability of event A, so we're going to look at the frequency of this event over N, the total number of observations. So coming to the table, at least 2 times per month. So 2 or more times per month would be those 3 categories. So that's my event A. And then I'm just going to add up how many adults were in each of those categories. So 15 plus 3 plus 2 are the number of adults that go to the movies at least 2 times per month. And that's out of a total of 25 observed adults, or 25 adults that responded. So 20 over 25. And I'll go ahead and leave it as a fraction. As always, we can do decimal or percents. And we could reduce as well, but we don't need to here, keeping in mind that the denominator tells us the total in the study, so it's kind of useful to see it in that form anyway. All right, B. So probability of event B. So an adult goes to the movies at most 7 times per month. So at most 7 means 7 is the max. So 7 or fewer times per month. And I'm just going to go ahead and bracket those categories. So 7 or fewer, that would be my event B. So the probability of event B, again, just frequency over N. So I'll add up the people in those 3 categories. So 5 plus 15 plus 3 divided by our 25 adults. And that probability will be 23 out of 25. All right, let's take a look at another one. And here we're going to address the concept of union and intersection. But first we'll start here. It's a study on diseased trees. And they took a random sample of 200 trees in a forest. And based on this data, we'll be finding some experimental probabilities. So let's just look at a summary here of what they kept track of. So they kept track of 2 properties: the size of the tree, large, medium, small, and the disease status of the tree, disease-free, doubtful, or definitely diseased. And they've done some totaling for us. All right, so there's the 200 trees broken down by their size and their disease status. So when you add those values in either direction, you'll get the 200 trees. All right, so we want to estimate the probability that a tree in this forest is medium. So the total medium, 46 plus 32 plus 14, they did for us and got 52. I'm still going to just go ahead and make a note of that though. So for medium, if we take 46 trees plus 32 trees plus 14 trees, that's where they got the 92 trees. So 92 out of those 200 trees are medium. All right, so that's our experimental probability. And then the probability of a diseased tree. So let me go ahead and also just make a note here of where they got that value, the total. So now we're looking at the diseased column. So 15 plus 14 plus 8. So I'm just going to switch color here. So 15 plus 14 plus 8. And they added that for us and got 37. All right, So the experimental probability of a diseased tree, 37 out of 200. All right, now we go to intersection. So intersection, those outcomes that are common to both sets. So we're going to look at the probability that the tree meets both conditions. It's medium and it's a diseased tree. So I'm also going to do some circling over here. So there were the diseased trees, the 15 plus 14 plus 8. And here are my medium trees, the 46 plus 32 plus 14. So when we say and in probability, we mean count outcomes that are common to both sets. So now I can see here that 14 trees met the condition of being diseased, and they also met the condition of being a medium tree. So 14 trees meet both conditions. I can also see that here, when I added up the medium trees, I included the 14. And when I added up diseased trees, I included those 14 trees. So 14 trees out of the 200 satisfy both conditions. So they're part of both sets. All right, so that's intersection. And then union. These are going to be outcomes made by combining the sets, and we say the word or. So if I want to know the probability that a tree is either medium or diseased, we'll include any tree that's medium along with any tree that's diseased. So for or, I like to say along with, because we combine the two groups. So what I'll point out here is if I take all the medium trees, there were 92. I'm going to write that number down. So 92 would be all the medium ones, along with, so adding then all the diseased trees. So the diseased trees, there were 37. But if I do add those two values, 92 and 37, both of those values include those 14 trees. So if we add 92 and 37, the 14 trees are counted twice. We call it double counting. So we don't want to count these trees two different times. So what we do is we take the total, the 92, plus the total 37. And then what we do is subtract any trees that were in that intersection. Those will be the ones that were part of both groups that would have been double counted. So to get us to the correct answer, we can take the total, so the total and the total, as long as we remember to subtract the trees that were part of both groups, and then that will be out of, again, 200 trees. All right, and I'll just do that on the calculator here. 92 plus 37, subtract 14. So 115 trees are either medium or they're diseased, or they're both. So or will also always include any trees that are both. All right, and we'll revisit intersection and union again for sure. But what we'll do next is go on to the next probability approach. So rather than experimental, where we collected data, we're going to move on to classical. So the classical approach, it's also called theoretical probability. We don't actually have to collect data. We're going to be able to find probabilities based on what is known as the sample space. So we'll start here with a random experiment. So a random experiment is a chance process that leads to well-defined results called outcomes, like spinning a spinner would be a random experiment. The sample space, we'll use capital S. The sample space for an experiment is the set of all possible outcomes. So everything that could possibly occur, and then an event will consist of a set of those outcomes. So let's go ahead and I'll get to the spinner in a bit here, but let me show you this one, number one. All right, so Rita is going to watch a movie at random from her collection. She has 4 comedies, 5 action, and 3 dramas, and we want to find the probability that she selects a drama. All right, so notation here, N of S, so lowercase n for number of, S is sample space. So I want to first find the number of items in the sample space. So in other words, everything that could possibly happen. So in Rita's case, how many different movies are possible? So she has 4 comedies plus 5 action plus 3 drama. So the number of movies she has, the number of items in her sample space is 12. And then the number of those that are drama, she has 3 dramas. So just leading you into some notation here. So for classical probability, the probability of an event, in this case, getting a drama, so we'll do D for drama. So the rule says we take the number of items that are in the particular event, so number of outcomes in the event, and divide by the number of outcomes in our sample space. And I'm sorry, I wrote E there. I'm going to switch that to a D for drama. So the number of movies in this case that are drama over the number of items in the sample space. All right, so that was a lot of writing to just get to this answer. She has 3 dramas out of a total of 12 movies, so a 3 in 12 chance. And I'm going to go ahead and write that as a decimal as well. So if you do 3 divided by 12, that is 0.25. And I'll go ahead and write it as a percent. So this is just to practice and remind you that we can write probabilities in different forms. And we could reduce the fraction as well, but I'm just going to leave it. So 3 out of 12, 0.25, a 25% chance she'll pick a drama. All right, number 2. So in an aquarium, there are 16 large fish and 4 small fish, and half of the large fish are red. 1 fish is selected at random. We'll find the probability that it is a large red fish. In other words, it is both large and it's red. So it satisfies both conditions. So we'll start with our sample space. So total number of fish in this case that are possible. If we pick a fish at random, so 16 large plus 4 small, we've got 20 fish. And the number of them that are large fish and also meet the condition of being red. Well, we have 16 large fish, and they say half of those large fish are red. So half of 16 would be 8. So we have 8 large red fish. And so our probability that it is large and red, so that it meets both conditions. And now I'm just going to write the answer here. So large and red, we have 8 fish out of the 20 that satisfy both conditions. And I'll go ahead and do this one more time here, just going through the different ways that we can write that answer. So fraction 8 over 20, decimal 0.4, and then 40%. All right, and then we won't keep writing it in all 3 forms moving forward all the time, but just practice there. All right, and then the next one, when we deal with classical, so classical or theoretical probability, we often see things like spinning a spinner, and the spinner needs to have equally sliced regions. So we need each possible outcome to be equally likely, as we're working here with our classical probability. And they tell us we have 2 blue slices, 1 red, and 3 yellow. So when we spin the spinner, we'll look at some theoretical or classical probabilities of landing on each color. So first, let's make a note here, the number of items in our sample space. So the number of regions that the spinner could land on, 6 regions, so 6 possible outcomes in our sample space. And then the probability of landing on a blue region, well, 2 outcomes make up that event. So 2 out of the 6 are blue, so there's your blue probability. And then red, there's 1 red region out of 6. And yellow, there's 3 yellow regions out of 6 regions. And then I'll make a note here that will be important to us later, that when we add those values together, so we have a common denominator of 6. So when we're adding fractions, common denominator stays the same. And then when you add the numerators, 2 plus 1 plus 3 is 6. So in other words, the probability of landing on a blue, a red, or a yellow is 1. or 100%. So 100% chance you'll land on one of those three colors when you spin your spinner. All right, so that's our classical approach, and we'll take a look at how this ties to the experimental approach that we saw earlier coming up.